Hello Math 1316 students, welcome to Trigonometry. Before starting anything, however, let's begin with some discussion on preliminaries. Very basic preliminaries, so it'll be short. I plan to complete everything within 15 minutes, at least that's my goal. Okay, let's begin with section 1, sets of numbers. Set notation. We can use roster notation or set builder notation, and then element notation like this, and subset notation like that, and not element, not a subset. Yeah, those kind of notation should be all comfortable to you. Sets of numbers, NWZQRC with double stroke font. Most of the time, the default set of numbers for everything for this course is going to be R, set of all real numbers. Sometimes, however, we are going to go beyond and we are going to consider complex numbers here in this course too. But rarely. Most of the time, just R, the set of all real numbers. Intervals. Need I say more? Okay, alright, some visualizations. Closed interval, the first one. The open interval, the second one, and solid dot means bracket, it's part of the set. Empty dot means parentheses, strict inequality, is not part of the set. And then half open and half closed intervals like that. Next, algebra of sets, union, A or B. Intersection, A and B. Complement, not A, all except A. And some difference of sets, A but not B, this crescent region, and B but not A. Again, we are going to get a crescent region like this. Okay, so much for algebra of sets as well, and let's move on to section 2. Properties of real numbers, part 1, the basic properties. Just arithmetic properties. First, the properties associated to addition and multiplication. Is everybody all totally, completely comfortable with all these? You should. Next, order property. That too should be totally and completely comfortable to everybody. Here I'm using the term XOR. What do you mean by that? That means exclusively OR. If you have any pair of real numbers A and B, A is less than B, or A is greater than B, or A and B are equal to each other exclusively. One and only one of those three will hold. And then the transitivity, and then preserving the addition. Adding the same real number to both left-hand side and right-hand side will not change the direction of the inequality. It'll stay as same inequality. Same for multiplying any positive real number. But if you multiply a negative real number, then you have to flip the direction of the inequality. The last one here is not one of the basic properties, however, because we can actually prove it from the other two. How to do that? Well, if you're interested, you can try on your own. It's not difficult, but I'm not going to waste class time on that. Final property, the completeness property. The set of all real numbers completely fills up the number line. What do you mean by that? Thanks to this property here, trichotomy and transitivity, every rational numbers can be arranged along a line too. But they do not fill up entire number line. Set of real numbers do. I just misspoke a real line. That's because number line corresponds to the set of all real numbers, so we usually call it real line. So there's no such thing called rational line or irrational line. Always real line. So number line is real line. Here's some visualization. Open interval, yeah, along a line. Oh, that's closed interval. That's open interval. Anyway, these are one-dimensional example. And here are some two-dimensional examples. We can define Cartesian coordinate system, which identifies each point on the plane through a pair of real numbers using this scheme. X is rightward distance, y is upward distance from the origin, 0, 0. And here are some examples. Blue, red, green, and brown points. So here, both x and y coordinate are positive. Here, x is negative, y is positive. X and y are both negative. Here, finally, x is positive, y is negative. And using those properties, we divide the plane, the Cartesian coordinate plane, into 4 quadrants like this. Quadrants 1, 2, 3, and 4. And then, of course, there are coordinate axes, x-axis, y-axis, given by x, 0, and 0, y. We can do all those because of the third property, the completeness property. There's one-to-one correspondence between any point, any point on a line versus a real number. And then we have 2 lines, horizontal and vertical. So we have one-to-one correspondence between any pair of real numbers versus any point on a line, any point on a plane, excuse me. So that allows us to do the geometry based upon real number arithmetic. And we're going to use that a lot in this course because the trigonometry, especially the college level trigonometry, is based heavily upon the Cartesian coordinate system. Okay, next, some arithmetic rules. Subtraction and division are defined as the inverse operations of addition and multiplication, respectively. Alright, that's easy. Some properties of 0. Okay, something over 0 is undefined, remember that. Properties of 1. Oh, that's too easy, right? Properties of sign. Again, elementary. In a little bit higher level course, we're going to prove these, but that's not what we're going to do here. So please prepare to use these properties whenever necessary. A little bit more about algebra. Algebra of fractions. Okay. If you multiply 2 fractions, that means multiply the numerators and denominators. Division means multiplying the reciprocal. And then, if you have to add, you'll have to take common denominator. Oh, what's going on here? And if you have to divide, no, that's not division. This is, what is it? It's a simplification. Yeah, if you have a fraction inside a fraction, then usually it's a good idea to simplify it off and then just come up with a single fraction. What do? Multiply the LCD, the least common denominator of everything, and then kill off all the denominators inside a fraction, and we have just one fraction left. We have been doing this a lot in elementary and intermediate algebra. Absolute value. Okay, alright. Yeah. And then exponents. Okay, alright. Exponents are defined as repeated multiplication of a, and we can do that whenever a is non-zero. How about a to the 0 power? That means we didn't multiply any of those starting from 1, so a to the 0 power is 1. Remember, a to the 0 power is 1, not 0. Negative first power, we define it as reciprocal, and then radical is defined like this. In this case, actually, it's better to define a as positive because I don't have to consider a negative number inside some even radical. Anyway, based upon these, we'll have these exponential laws, and also beware of some common mistakes. Yeah, works for addition like these. We can separate the numerator, but we cannot separate the denominator or power or radical. We can do those for multiplications. These are common mistakes. Okay, all right, we have sufficient time, so let's go a bit further. All right, let's go to section 5. All right, exponent laws, yeah. All good? All right, let's go to section 5, some geometry essentials. First, Pythagorean theorem. Whenever you have a right triangle, think about Pythagorean theorem. A squared plus b squared is equal to c squared, where c is the hypotenuse. How do you prove that? Most of the time, I'm not going to emphasize geometrical proof a lot, but this is one of those exceptions. I think you should know this. There are many different ways to prove Pythagorean theorem, but this one I think is the easiest of them all. And not surprisingly, our textbook has that too. I mean, our algebra textbook. Wait a minute, we're using the same textbook, Algebra and Trigonometry. All right, our textbook has this. So, take this right triangle here and then consider 4 copies of the same right triangle and then arrange like this so that we get a square. A in one side, B on the other side. B here, so A there. So what's the area of this square? Horizontally A plus B, vertically also A plus B, so area of this big square is A plus B, this total quantity squared. Now, on the other hand, we can consider this big square as the area of this 4 copies of this original right triangle. So that area is 1/2 AB, 1/2 times horizontal times vertical, 1/2 base times height, and there are 4 copies of those, so you have 2AB. That's the red part. And how about the blue part? That's c squared, hypotenuse squared. So the right-hand side turns out to be c squared plus 2ab, and left-hand side is this complete square, a plus b, this total quantity squared. Fold it out, and you get this expansion, a squared plus 2ab plus b squared, and you can kill off this plus 2ab and that plus 2ab, subtract both of those out, and you end up with the desired result, a squared plus b squared equal to c squared. There are other methods of proof too, and this one is in our textbook too, using a minus b squared instead of a plus b squared. Similar, but I prefer the previous explanation here. And then, there's some more as well, only for interested students. And then, of course, there got to be many more, actually, a dozen more maybe. I don't know how many different proofs were discovered. There's a recent discovery too by high school students, by the way. All right, some 2D figures. All right, area formula for rectangle, A times B. All right, that's easy. Area formula for triangle, base times height times 1/2. And then we have proofs as well here, if you're interested. For acute triangle, half of this rectangle. And then for obtuse triangle, we can use the distributive property, this blue minus green. Parallelogram, the area is base times height. And the proof, well, cut off and then paste it, and then you get a rectangle. Trapezoid, 1/2 times a plus b times height. And then you can prove it by patching together a copy and then getting the half of the area of this parallelogram. Finally, area of a circle. And then the sketch of proof, I gave you this kind of argument from the textbook. The details are left to the students. So eventually in limiting case, the area of the circle will resemble the area of the rectangle. So we have pi r squared in the end. So that's the essential preliminaries. That's it.